So the first speaker is Richard Kesler. So Richard is a research engineer with the Fire Safety Research Institute, part of ULRI Research Institute, based out of Columbia, Maryland, USA. So he has worked to characterize the thermal and chemical properties of fireground and understand how firefighting personal protective equipment performs under these conditions. So Richard served as a member of the Survey, Illinois Fire Department for more than 10 years. It ranks up to assistant chief. Richard holds a PhD in kinesiology and MS and BS degrees in bioengineering from the University of Illinois. Okay, so Richard, so the floor is yours.
Thanks for the introduction, Jimping, and thank you to Svetlana and Hamed and the entire team there for hosting this workshop. So I wanted to go over a study that our group at the Fire Safety Research Institute has recently ran. I'm going to discuss a small portion of that, which is the chemical characterization of vehicle fires, but there's much more to the study that looked at the thermal properties of fires involving internal combustion engine vehicles and electric vehicles, as well as the effectiveness of different suppression techniques, different thermal characteristics, and all of that. So I'll be focusing just on the chemical piece here. So next slide, please. So the specific research questions we wanted to address are what are the hazards with electric vehicle fires? And in order to put those into context, we needed to know if they differ from the hazards that already exist on the roadways with internal combustion engine vehicles. And then another question we had is how do these hazards vary by position as you're around the vehicle, in the plume, as the smoke produced by the vehicles spreads? Is there different risks around the areas of the vehicle? Next slide, please. So to do that, we conducted a number of tests, electric vehicle tests, including internal combustion engine vehicle tests, at a large-scale fire lab just outside of Chicago in Northbrook, Illinois. As I mentioned and alluded to, we took measures of the fire behavior, trying to understand how what the thermal properties were, the risks of fire transfer, the heat flux, temperatures around the vehicle, and all those measurements, and we're working on reporting those later this fall. We also had turnout gear swatches, which I'll talk a little bit more about, but those were placed around the vehicle, and we're looking at the characterization of the contaminants that get onto the turnout gear, and then how those contaminants can be removed through laundering and other cleaning practices. We monitored the plume, taking samples of the smoke for various compounds, which I'll explain in more detail, and then did some analysis at the ground level or the operational level where firefighters or other responders might be. Next slide. Thank you. So we set up these sampling stations, and I'll go through a little bit of what's in that at multiple positions around the vehicle. So here you can see the yellow rectangles in front of and behind the vehicle. They're positioned about 3 meters off of the front and 4.5 meters off the back of the vehicle. And these sampling stations contained a number of different metrics. I'll just discuss a few of them. But here you can see the black rectangular turnout gear swatches across the top. There's 4 of those. The large instrument on the left, wrapped in aluminum foil, is a heat flux gauge, so we could get a heat intensity. We have a pan at the bottom, a flat sheet, to collect solid particulate that deposited around the vehicle, which are all going to be reported elsewhere. But today, if you click to the next, I'm going to be highlighting our active sampling techniques. So we used active sampling pumps here to measure the compounds that are listed there: benzene, toluene, ethylbenzene, xylene, aldehydes, metals, acid gases. We measured isocyanates, PAHs, and then inhalable particulates, all with these active sampling methods. And so these pull air from the environment through the media, which is the top of the gray box there, and then we send those media off for analysis to quantify what's in the environment. And one important note is that these will collect samples across the entire duration of the test. So we're looking at average concentrations in the air from the time the fire is ignited until everything that can combust has, and we reach the end of flaming combustion. Next. We also had passive sampling measures, so we used silicone wristbands placed around the vehicle and in the plume, which passively collect both vapor and particulate, and then we analyzed those. So I'll discuss that in a little more detail later on. Next slide. We took both the active sampling and passive sampling measurements and fixed them to a position above the vehicle. So what you see in the picture on the right is the vehicle placed on a platform, which was used in this case to had scales in each of the four corners so we could measure mass loss from the vehicle. And then the smoke plume went up into the curtain you see above. That curtain's hung just a few centimeters below the ceiling so that we could kind of funnel the smoke produced by the vehicle. And then the small gray box up there at the top where the arrow's pointing is our sampling media. So we have a large turnout gear swatch and then both the active and passive sampling media up there. Next slide. Here's the list of the vehicles we tested. In this comparison, we have 6 EVs and 3 internal combustion engine vehicles. The box here highlights the range of the oh, sorry, that went fast, but you can see the battery sizes there ranging from 28 kilowatt hours up to 91 kilowatt hours. And importantly, these are on the smaller end of the battery sizes, or I guess the more common end, although we do see consumer vehicles that are in excess of 200 kilowatt hours available for sale in the United States right now. So we are a little bit on the smaller end with our testing, and that should be noted. The box that you see there now highlights 3 vehicles that all had the same basic car model, just with different propulsion systems. So as we go through any of those that have the red indicator, just note that those are the same vehicle across different propulsion systems. Next slide. In terms of timing of how long the burns took, the total column height here is from the start of ignition through the conclusion of combustion until, like I said, the end of flaming combustion. And what we see is that the EVs and the internal combustion engine vehicles had some slight differences. The EVs from again, ignition of the pilot burner until conclusion we're about an hour, 102 minutes versus 65 for the internal combustion engine vehicles. And if you advance one, please. But when we look at the actual time, just the gray portions of the bar, which is the time from when the flame transferred to the vehicle until the end of flaming combustion, we see that the differences was really much smaller and potentially not really statistically significantly different. We see a difference of only 5 minutes from the time the fire reached the vehicle until the time flaming combustion had concluded. Next slide. Looking at the mass loss of the vehicle, the EVs had about 80 kilograms more of mass lost by the end of it. And what that means from an exposure standpoint is that 80 more kilograms of material were produced into the smoke and generated into that cloud that are potentially available to contaminate the environment or the firefighters or other responders. Next slide, please. So I will walk through this plot because this is very similar plot that much of our data are presented as. So what we have is on the left, the different compounds we tested for both EVs and then internal combustion engine vehicles. Each of the circles represents a specific electric vehicle, and then each of the triangles represents a specific internal combustion engine vehicle. The X's represent the median for each group. And then, as I noted, the red symbols, either circles or triangles, represent the same vehicle just with different drivetrains. And so what this plot is showing is the different metals that make up the battery composition. So we've got lithium, obviously, in the batteries, and then manganese, cobalt, and nickel. And what we see, not particularly surprisingly, is that in the electric vehicles, these compounds are substantially higher. And if you advance one, please. And I want to point out the scale here because these are on the order of 5 to 10,000 micrograms per cubic meter, or 5 milligrams per cubic meter, and that's relevant because as we advance to the next slide, we see that the scale here only goes up to about 1,200 micrograms per meter cube. These are other metals that are present in the vehicles, but aren't typically part of the battery construction. So antimony, aluminum, lead, copper. We see, some differences in the electric vehicles. Lead with the lead acid batteries of internal combustion engine vehicles tends to be higher there. Not much differences in copper, but much more similar between the two vehicle types. Next slide, please. If we look at those BTEX compounds that I mentioned earlier, specifically in the plume, we see that there's some pretty broad ranges between the different makes and models of the vehicles, but there's really no distinct differences between internal combustion and electric vehicles in terms of the fires from a BTEX's standpoint. Again, those are all from the plume. And if we go to the next slide, yep. We look at benzene by the different locations. So if we look at the 10-foot or 3-meter position, we see that there's not a lot of differences, and those benzene compounds are on the order of 0 to 1 milligrams per meter cubed. It's the same at the 15 or 4.5-meter location. And then when we look at the plume, not surprisingly, we see substantially higher concentrations of benzene, which is a known carcinogen present in the plume. So obviously we don't expect firefighters to be working in the plume environment, but in terms of different weather conditions, we may have exposure to nearby populations, or if this is in a parking garage or some other confined space, that plume could certainly be exposing individuals. Next slide, please. Acid gases, we certainly have heard that there's a lot of concern over acid gases as the fire service responds. So we looked at those, and I'll mention in a second that we also looked at the particulates of some of these acid gases. So here we're looking in the plume at hydrogen fluoride, HCl, HCN, and we see a broad range of differences between vehicles, but we see a lot of overlap between the EVs and the internal combustion engine vehicles. As we go to the next slide, here we're looking at the differences between hydrogen fluoride and then fluoride as a particulate, or the ion. And this is where we really start to see some of those differences. So at both 3 meters or 10 feet and 4.5 meters, 15 feet, we see that the EVs have substantially higher fluoride particulate than the internal combustion engine vehicle counterparts. And that carries through also to the plume. Next slide. We also used, as I mentioned, the passive samplers. So we used, I won't go through this entire slide, but based on some calculations, we're able to get a calculated air concentration based on the levels of compounds we detect on the samplers. So next slide. So I'll go through the PAHs we discussed. This list is the U.S. Environmental Protection Agency's 16 priority PAHs, 10 of which are possibly, probably, or known carcinogens. So the next slide here is the summation of those 16 PAHs in terms of their concentrations around the vehicle. And what we see is that there's not a lot of differences. Some of the internal combustion engine vehicles are actually slightly higher, potentially because we did fill the fuel tanks for these vehicles, so they were full of gasoline. I think each one had a 50-liter capacity, so as that fuel tank failed and that fuel became available to the fire, we certainly expect high levels of hydrocarbons to be produced. Next slide. So just to recap, between the vehicles, we had a similar burn duration, although the EVs took a little bit longer to get started with our gas burner. We did have greater mass loss with the EVs. As expected, there were high levels of the nickel, manganese, cobalt, and lithium metals in EVs, which are used in the manufacturing and construction of the batteries. The acid gases were similar across the vehicles, although fluoride particulate was elevated, which is a major concern and can be a known irritant and potentially toxic compound. And then PAHs were similar also, although, again, as I mentioned, with the fuel potentially resulting in slightly higher medians in those internal combustion engine vehicles. Next slide, please. So where are we going now? We've just wrapped up testing, looking at suppression of these vehicles. So in all those tests, again, there was no firefighting intervention. We let the fires run from ignition all the way through the end of flaming combustion. But we have run the tests and are currently analyzing the data to look at standard firefighting techniques. So that's just the water and hose line. We've looked at EV-specific techniques, applying fire blankets, utilizing undercar nozzles, placing additives in the water, and understanding how those impact contamination. And then through all these, we've collected the same measures, but we've also placed a number of those measures on the firefighters doing the suppression, and then collected the runoff water to see if there's any differences in what's produced into the water or on the firefighters. Next slide. So with that, just want to acknowledge Adam Bowerwee, Gavin Horn, Chandler Probert, Nate Sauer, our research team who's worked on this project, as well as the entire FSRI team that made these massive studies happen. They were conducted in partnership with our team sister organization at UL Solutions. And then much of our assessments wouldn't be possible without our partners at Duke in North Carolina, as well as the National Institute for Occupational Safety and Health. So just want to thank them. And then I'll close by just saying that QR code will pull up my contact information. If you have any questions, please feel free to scan there, and I would be happy to have further discussions offline. Thank you.